So another place that we use logarithmic differentiation to figure out the derivative is when we're dealing with tower functions. And what we mean when we say tower functions, that's when we have a variable as part of the base and as part of the exponent. Remember, a polynomial, you have the variable as part of the base. It's being raised to a fixed power. There's the sums and differences, things like that, like x squared plus 3x minus 7. And in exponential functions, we have the variable being part of the exponent, but the base is fixed, like 2 to the x, and 3 to the x, and e to the x. While in a tower function, the variable is showing up both in the base and in the exponent. Things like x to the x, sine x to the tangent x, or 1 plus 1 over x to the x. Okay, problems like these. And we'd still like to be able to talk about the derivative of this kind of function. We'd still like to be able to talk about the derivative of this kind of function. Unfortunately, x to the x is neither a polynomial or a power function, so our power rule, multiply the exponent, decrease it by 1. Think about that if you tried to do that. Multiply by x, and then decrease it by 1, you'd have x minus 1. Well, then you'd be back to just x to the x, because multiplying x times x to the x minus 1, right, you'd add 1 to the exponent, you get back to x to the x, so it kind of doesn't work. And then think about it in terms of an exponential function. How do we think about that? Okay, same thing with all these other ones. Well, logarithmic differentiation gives us a really nice way to do the derivatives of these functions. So, writing that down first as y equals x to the x. My computer was lagging there for a second. We apply ln to both sides. So on the left-hand side, we get ln of y. On the right-hand side, we'd have ln of x to the x. And then we can make use on the right-hand side with our properties of logarithms. Pull the x out, the exponent one out, and we get ln of y equals x ln of x. Apologize, my video is lagging here. The screen broadcast is lagging for some reason. And then we can do the differentiation using implicit differentiation. So we'd say derivative of ln of y is just 1 over y times dy dx. On the right-hand side, we have x ln of x. So we use our product rule. X times the derivative of ln of x plus ln of x times the derivative of x. And then we can do a little bit of simplifying. So the x and 1 over x will cancel out to just be a 1. And then we'll have just plus ln of x. And then we just bring the y over, which is x to the x. So we'll have dy dx equals, bringing the y over from the 1 over y, we'll make that x to the x times 1 plus ln of x. And now we've done the derivative of that tower function. So it turns out the derivative of x to the x is itself times 1 plus ln of x. So that tells us the growth rate of the x to the x function, which I want you to notice is quicker as x gets bigger and bigger than an e to the x function. E to the x is its own growth rate function. But notice x to the x is also its own growth rate. Plus it has a multiplier that's greater than 1, right? ln of x here, when x is positive, once x gets beyond 2, 3, 4, and so on, ln of x is greater than 1. ln of x is positive. And so we're dealing with is greater than 1, sorry. So we're dealing with something that's got a bigger and bigger multiplier the further to the right we grow. So it turns out this x to the x, which is sometimes called the super exponential, it outperforms or will actually outgrow an e to the x function. Now that's something you'll run into and talk a little bit more about in calculus too. But here we just wanted to talk about how we could do the derivative of these tower functions. And the idea is to use our logarithmic differentiation.